So what we would like is to have v expressed in terms of only h without the b variable in here. So if we could find a relationship between b and h, that would be very useful. All right, so what do we have? Well, much like other problems, we have triangles, and we have proportionality between triangles because we have this one, the smaller triangle, stuck inside the larger triangle here, which is the entirety of the trough. And there's the whole trough triangle, and you've got the water triangle. I should have inverted the colors, but anyway, you've got the water triangle embedded inside of that one. Yeah, so there's some proportionality going on here. And it should be safe to say that this leg of the outer triangle is to this leg of the inner triangle, right? 3 is to B. Just move up a little bit here. 3 is to B. And now we can compare the heights, right? The base is to the base, right? 3 is to B. What the outer height, 4, is to H, right? Outer height to the inner height. 4 is to H. All right? So now we have a relationship between B and H, which is extremely useful for this problem. So we want to write B in terms of H. Okay? So the easiest thing to do is just perhaps flip them both, right? Don't write it like that. Write it as B on 3 equals H on 4. And then just multiply both sides by 3. So you would have B in terms of H. B is 3/4 H always in this problem. No escaping it. Okay? B is always 3/4 H. This base here is always got the 3/4 of this height. May not be so obvious from the proportionality of my picture, but the truth of it is so. All right, so now I'm going to use this. I'm going to substitute into this volumetric equation here, and now have volume and height only. B is gone, right? So this is the full relationship we were looking for between the volume and the height. So now we have volume is always equal to the 1/2 and the 10 all combined together into a 5. So we have 5. B is 3/4 H times the other H that was already there. All right, so 15/4 H squared. Great, we got it. Now we take the derivatives, we will be able to find dH dt. It's going to come out of the right-hand side. dV is already known, right? On the left-hand side, it's going to be a 5. So we're good to go. Just finish off the problem now. But that special relationship we had to find here to fill in to the volume equation is an extra piece that other problems may not have had so far. So it's something to be aware of. All right, so dV dt should be the same as 15/4. The derivative of H squared with respect to time will be 2H dH dt. Again, because this H function of time is stuck inside, right? It's an inner function to the squaring function. So square comes down, power goes down by 1 to the first power, the inner function stays the same. You take the derivative of the inner function and multiply on the outside to complete chain rule. I can cancel this 2 with this 4 to some degree. So we have dV dt equals 15/2 H dH dt. I want dH dt by itself, so I'm going to move this to the other side by reciprocation. Okay, so we should have now dV dt times the reciprocal of this, which should be 2 on 15H. And that should be equal to what we were trying to find all along, which is dH dt. Okay? So now if we just calculate dH dt, when h is 1, which is what we wanted in the first place, we should have dh dt when h equals 1 will be 2 over 15 times 1 times the derivative of the volume, which we said was 5. And then 5 and 15 cancels, you get a 3. So we have 2/3. 2/3 what? Well, it's the change of height with respect to time. And the units above were measured in meters and minutes for length and time respectively. So it should be 2/3 meters per minute. And we have our answer.